in this video, basically, like what you will be doing is that you will understand the fundamental theorem of calculus, and then explore why this is useful. So, like, I will go through the details, and then I will show you by the end of the video why this is useful. This video actually it's an overview over like these three module: differential calculus, integral calculus, and differential equation. Like this lesson, like this video, is just like an overview of what we will be covering over like the next 8 weeks. So if you don't understand much of the material covered in this video, that's fine. Don't worry, don't be overwhelmed, don't get discouraged, because you will spend the next 8 weeks learning all these things in detail, and by the end of like in 2 months from now, you'll see, like, you'll look back at this lesson and you say, oh, I mean, I understand this is easy, and I appreciate, for example, the fundamental theory of calculus and how it, for example, connect to conservation laws, and how why these things are useful. So hopefully in 8 weeks from now you will appreciate this. Okay, so without further talking, I've talked a lot. Let's just get started with this interesting material. So calculus is related mathematical concept of differentiation and integration. And again, I know some of you didn't might have heard this term like differentiation and integration, but they don't know what it is. They don't know like what is differentiation and what is integration. Yeah. So that's what I will try to explain now. So let's so the differentiation basically like or like a derivative, or let's just look here. Like, let's look at this function. Yeah. So we have here a function. Yeah. So this is like our dependent variable, like f of x could be like whatever that is, and here is our like independent variable x. So basically we here have a function of x, like this is like a function of x, any function we have here of x. Yeah. And then you see this function here is like decreasing, 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 and then here is like increasing, 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 and increasing. Yeah. So the rate of how this function is increasing or decreasing, we call this like the slope, like at a point. Yeah. So the rate at the point of how this, at each point, yeah, how this function is increasing or decreasing, we call this like the slope. Yeah. So the slope of, so if we want to visualize uh, this rate, we can like draw a tangent here. Okay. So basically, like if we draw a tangent here, yeah, if we draw like a tangent here to visualize the rate of how this function is like increasing or decreasing, the slope of this tangent, yeah, that will be like a visualization for the rate of change. Yeah. And the derivative, okay, derivative, and I will explain to you that in a minute. That would be the slope of this tangent. So if I told you, if I just asked you a question, uh, what is like the slope at this point? Like, what is the rate of a change of this function at this point, or what is the slope of this tangent at this point? Like, how could you like find the slope of this tangent, like the rate of a change, like here at this point? So how can you do this? Well, one way you can do this, we know how to find the slope. So one way we can do this, so you have some tools here. Maybe I will just like like draw a line. Oops, what's going on? Oh, undo, undo, undo. Okay, let's see. One thing I can just come here, I can just like draw, like let's say here, secant line. Okay, I'll just, here we go. I will just like draw like secant line here. Okay, so I will just like draw like a secant line here. Okay, uh, and like with this like secant line, I can find like the slope of this secant line. Yeah, and then we know how to find like the slope of a line. Yeah, so the slope of a line, we know this like we know like how to find the slope of a line, that is equal like to dy over dx. That's like how like this. Let me make some space here. That's like dy over dx. So dy in that case that would be, so here so here like here we have, let's say here we have like, let's just go like this is x and this is like x plus delta x line here. This is like this distance here, like delta x. Yeah. So here we have like x and x plus like delta x, and this is like the delta x here. Yeah. And similarly, that would be here. That would be like at this point. That would be like f of x, and like at this point here we have like f of x plus delta x. Yeah, we have f of x plus delta x. So what is the slope of the line? Delta y over delta x. So delta y, that would be like this guy minus this guy. So that would be f of x delta x minus f of x divided by divided by like this guy, like x, like x plus delta x minus delta x. That would be like delta x divided by like delta x. Yeah. So divided by this guy. So basically that is the slope of this line. So we draw like this secant line here, and the slope of this secant line here, it would be like f of x plus delta x minus f of x, yeah, divided by like the distance. Yeah, so the difference in y, like, so the difference of this guy from this guy here, so the difference, like the difference from here to here, divided by the distance, divided by the difference from here to here. Basically, like the difference from here to here divided by the difference from here to here, that will give you the slope of this line. Yeah, let me delete all these things. Yeah, be more clear. That would basically be like the difference. Oops, I deleted. I didn't want to delete this guy. That would be basically, delete this guy also. Oops, I want to delete this guy. That would be the slope of this line. Okay. Does this looks good? Well, it's good. I mean, the only problem is, that's the only problem, is that the slope of this secant line, which we have here, is not exactly equal to the slope of this tangent line. So can we solve this problem? Can we like, so it is an approximation. It's not a bad approximation, but it's not exactly similar. So to solve this problem, yes, we can solve this problem. Let's just uh, make like this line a little bit shorter. Yeah. So if we make this line a little bit shorter, yeah, here, and then like we make a point here. Delete this guy. We like bring this point here. Yeah. This guy will come here. So now, like you see, like as we make this delta x shorter, you see like these two things are approaching together. Let me make it even a little bit shorter, like smaller, like much smaller. Like see, I'm decreasing this guy. See, as like I'm making this guy much smaller. You see how the slope of this line now is aligning and becoming the slope of this line. You see, like as I make this shorter, how it became like very aligned of this secant line. So it turns that there is like what we can do if like delta x, yeah, if delta x goes to zero, like we make like this distance very, very, very small, then the slope of this secant line will be exactly the slope of this tangent line. And in this case, so basically, like we can write something here. In this case, there is like a term for this. Let me delete these guys. I can like replace this delta x by over delta y with this d here, like with this derivative. This is called like a derivative, like what? This is like a derivative, like dy over dx. So I can replace the delta y over delta x with this derivative, and that would be equal, this derivative is equal to what? It's equal to this guy as the delta x goes to zero. So there is a way for writing this. So the limit of delta x as it goes to zero, yeah, then uh, we will have delta x. That's, I'm just copying what we have above, delta x over delta x. So that's the difference between like the difference approximation. So this guy is called like a difference approximation, dy over dx, which is equal to something like this, yeah. And then this is called like the derivative, yeah. So the derivative is dy over dx as the delta x is like this distance like goes to zero, then that's called the derivative. Okay, so that's called like the derivative of a function, which is like the rate of a change of a function. Derivative, it could be, there are different ways to write them. So like one way to write it, you can write it dy over like dx. That is equal to uh, f prime x. So f prime x, that is equal to dy over dx. That is also equal to, you can just say y prime, yeah. So you have like your function, so like your original function is like, let's say f of x, like y, it's equal f of x, yeah. The derivative of the function, the derivative of this function, the derivative of function means what? Means the rate of a change of this function at points, yeah, at any point. So that's like another function which would describe the, it's another continuous function that describes the rate of the change of this function at a point, at any point, yeah, along. So you can express it like dy over dx. You can express it f. Like, so when you see this prime, this means not the original function, it's the derivative of the function. When you see this y prime, it's not the original function, but the derivative of the function, yeah. So let me show you, like, let me help you, like, try to visualize this, yeah. So I have uh, so here, this is what I just like explained, like for this secant line, as this distance gets very small, then you can, the difference approximation can be written as derivative, okay. So here, let's visualize this. So you see here, this is my function. So you like see this blue thing here, that is like my function. So that is the function. And here, this is like the tangent of the function to visualize the rate of a change. And so you see here, like this f prime. So that's my original function. F prime, that is like the derivative of the function. And basically here I am calculating the derivative, the rate of change of this function. You see here the rate of change of this function is negative. Here it will be like 0, and here it is like positive. Like look at this number. Let's follow it when it start from the beginning. So you see here, this is like negative, negative, negative. Here it's almost like 0, and then it become positive, positive, positive. It's increasing. Here it's like very flat, so the rate of change here is very small. Like you see this number is very small because this is very flat. Here the rate of change, you see it's like still like small. Here it becomes steep, 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 steep. And then like if you are climbing in a mountain, and then you will go in this like deep slope, and you see very big rate of change here. Here like it's 0, and then here this is like if you are a mountain climber, for example, that would be a big cliff, and the rate of change here, the slope would be very high. So basically that's what uh, so this is the function, this is the derivative of the function. What the derivative of the function tells you is tells you like a slope at a point. Like so here at this point the slope is 0. The function is not changing. Here the slope is like small because the function is not steep. Here the slope is big, and here the slope of is or the rate of change is very big. Yeah, moving fast. Okay, so this is just like a visualization. And so calculus is the mathematical concepts of differentiation and integration. Okay, so differentiation, they uh, have to do with derivative, because like when I differentiate a function, what I get is I get this derivative, just as I showed you here. So like when I differentiate, like, so I have this function. If I differentiated this function, what will I get? I'll get this guy. Yeah. If I integrated this function, you know what will I get? I will get the area under this curve. And this is like the next part that I will be talking about. But if I differentiated this guy, I will get this. If you don't understand much, that's fine. I will repeat this again in the next lesson. This is just like an overview so that you get like a complete picture of like this module, like differential calculus, integral calculus, and differential equations, so that you know what we will be covering in this module. Okay, so let's go here. So in calculus, a related mathematical concept of differentiation is called like integration. So integration, like differentiation, what I'm doing, I'm finding like the rate of change, or like slope of the tangent at a point. In integration, like you can think about it like it's the opposite of differentiation, and I will show you this like in a moment. It's the opposite of differentiation, and you can think about it as like I'm finding like the area under this curve. And integration uh, integration, it will generally be presented so like this is like called like an integral. So here this is like integral. So here you see this is like kind of look like a sum, and that's exactly what to do, is like a summation. So you have like this integration symbol here, which looks like a sum, and then you have like f of x dx. So basically, if I integrated a function, so this is my function, I'm integrating it from here to here. This means I'm finding like the area under this curve. So here I have my function. This is like my independent variable, and then x, and integrating the function would be equivalent to finding the area under this curve, like what's accumulating under this function, basically. Yeah. So one is like the rate of a change of function, and the other is like what's accumulating under this function. Let me just do like a very quick example, very quick. Again, we will spend the next 8 weeks doing this in detail. If you don't understand this example, if you don't understand what we are doing, that's fine. Don't worry, don't panic, don't get overwhelmed. Uh, you will learn it like later in detail and in depth, but I just want to show you like here. So here, that is the fundamental basically theorem of calculus. So the fundamental theorem of calculus tells you this is like a derivative of the function. If you integrated, because remember, differentiation, that's the opposite Integrations, that's the opposite of differentiation. So the fundamental theorem of calculus tells you if you have a derivative of a function, the rate of a change of a function, if you integrated it, if you integrated that derivative, you'll get your original function back. That's all what this thing is telling you. So here I am like integrating from a to b over like dx, like little part of x, and what I am integrating is like the derivative of my function. What will I get? I will get the original function. If you don't understand this, that's fine. We will do this in detail over the next 8 weeks. So let's look at example. Yeah, let's look at example. So here, remember in the previous picture, like the previous animation, I showed you the function and I showed you the rate of a change of a function that we were plotting, but I never showed you the equation of this guy. So how can you find like the equation of this guy? So here I'm differentiating. So here I'm like differentiating this function. Like how could I find the derivative of this guy, like the derivative equation of this guy? Well, there is like a rule for it, which is basically like you bring this power, like you see this power here, you bring it here, and then you subtract -1 from here. So the rule is like there's like 3x to the power of 2. So that is like, so this is this function. Yeah. This is called like the first derivative of this function, which basically this is like the rate, or like this is my function, this is like the rate of a change of this function. Can I differentiate like this derivative again? Yes, why not? So like this is called like the second derivative of a function. So this is how it looks like. And this would mean like the rate of a change of the rate of a change. And like how do we do this? Again, like you bring this power down, so that would be like 2 times 3, that will be 6, and you subtract 1 from here, so that would be like x minus 1. Yeah. Can I do one more? Can I find like the rate of a change of the rate of a change of the rate of a change? Like that's called like the third derivative. Yeah, I mean, why not? I mean, it's fun to do it. Yeah. So I can say like d3y over dx3, and again that would be equal to what? Like you, this is like to the power of 1, so 1 times 6, that's 6, and then you subtract 1, then that would become x to the power of 0, and x to the power of 0 is that's 6. Yeah. So basically what I did here, I just like this called like the first derivative, the second derivative, the third derivative. Now how could can I get this guy back? Yes, I mean if you kept integrating all the way up, like so now if I integrated this guy, I will get this guy. If I integrated this guy, I will get this guy. And if I integrated this guy, as it's shown here, guess what I will get? I will get this guy. So let's do the integration. Yeah. So the integration means like I will be like integrating from 0 to x of, I'll be integrating this guy like d3y over dx3, for example. And I know that this is equal to 6. Yeah. So that's like 0 to x. I'm integrating like 6, and the integration of this guy. So like remember here, like when we integrated, what did we do? Like we subtracted like -1 from the power and multiplied here. Here we do the opposite. Here we add and divide. Like here subtract and multiply. Here we add and divide. So basically, if I integrated this guy, I will basically, so that's like x to the power of 0. Yeah, so I will just add 1 here, so that would be x to the power of 1, and then I will divide this by 1. So basically I will get 6x, and that's evaluated from 0 to x. See here, that's what I got. Yeah, like when I integrated this guy, this is what I got. So basically I just evaluate this guy from x to 0. So like how to do this evaluation? Just so that's basically would be like 6x minus 6 to 0. So basically I substitute the x here, and then that will give me like 6x, which is, what is 6x? Yeah, this guy. So exactly like here I'm differentiating. When I integrated this guy, like when I integrated the third derivative, I got the second derivative. Can I do it again here? Can I like, so now this is my, can I integrate from 0 to x d2y over dx squared? That would be like 0 to x, 6x. And if I integrated this guy, remember like how you do it, you add the power 1 here, so that would be x squared, and then you divide by 2, so that's like 2 divided by 6, that is like 3. And you evaluate this from 0 to x. What did I get here? Oh my god, I got this guy. Yeah? So if I evaluated this guy, I will get something like here. Like evaluate. Just do it the same here. Can I integrate this guy again? Yeah, why not? Let me integrate this guy again. So like, so I will be integrating. So now this guy is like my first derivative. So like I'm integrating like my dy over dx. So that is like from 0 to x, 3x squared. And like, remember the rule is like you add 1 here, and then you divide by 3. So you add 1 here, that would be x to the power 3. You divide by 3, then you get, what do you get? Get like x cubed to the power of 0. And then if you evaluated it from x to 0, then you will get like x cubed, which is like my guy here. Wow. So I just showed you like the fundamental theorem of calculus. If you don't understand much, that's fine. Don't worry, don't get overwhelmed, don't feel bad. We will do this in detail. I will repeat the same thing actually lesson again in the next video, but here I'm just giving you an overview of all the course. So in lesson 1, like what we will be doing like this guy here, like the differentiation. In lesson 2, we will be doing this guy here, which is called like the integration. So this is called like differentiation. What I did here, I differentiated the functions. When I differentiated this guy, I got the first derivative. When I differentiated the first derivative, I got the second derivative. When I differentiated the second derivative, I got the third derivative of this function. Here, this is like the fundamental theorem of calculus. Like if I, like this is my first derivative. Get back. This is like my first derivative here. If I integrated like my first derivative, what I will get this guy back. So basically, so here, like this is my dy of x. I substituted this guy here. Then I got my original function back here, which is basically this one. Okay. So I know like some of you are now thinking, I mean, why are we studying this? Like, why these things are important, or why these things are even like useful in life? I mean, who cares? I mean, who cares? Like, you have a function, you differentiated it to find like the rate of a change, and then you integrated it to find like accumulation or area or whatever. Yeah. I mean, why these things are useful? Okay. Let me show you why these things are useful, but I will do it step by step. Yeah. Here. This is just what we did before, yeah? Like, so you consider a spatially differentiable scalar function on one-dimensional system with bound like A and B. This is similar to what we did before. Yeah. So here, like, if this is again, like me recap, this is like I have a function u here, and this is like the derivative of my function. And if I integrated the derivative of my function, I'll get my function back. Yeah. So that is my dependent variable, and that would be here like that's my independent variable x. Okay, but what if this is like a vector function? Like vector function means that like this u is not only like a function of x, but it's like a function of x, let's say like space and time. Like this is something that's not only changing in space, as like I showed you like in the previous example, but it's also changing in space and time. So that would be like, this is a fundamental theorem of calculus. Would be the fundamental theorem of calculus, same thing as we did before, but for like a vector function, which means that like it has two independent variables, like space and time, like x and time. Is there like a more general form of this? Yeah, like just beyond like a two variable? Yeah, there is like a more general form of this. It looks like this. It's the same, like you see here's this guy. It's just like the same here. This looks like, this guy, I mean, you're probably wondering, oh my God, what is this like inverted delta? Like this inverted delta is called nabla, and this inverted delta with this dot, that's called like divergence, and that's vector calculus. And don't be afraid, don't be overwhelmed. I just want you to see the similarity here. So here's the similarity. Here now I have like my R is not just like changing like in space, like one dimensional space is changing in like X, Y, Z. So here, my R here, that's like a vector X, Y, and Z. And I can just like write the same thing, except like A from B will not be like an interval from X1 to X2, but that would be from area to an area. Yeah, so that would be from area 1 to like an area 2. And here, that will, the delta X will be like you integrate over, like that will not be delta X, that will be delta X, delta Y, delta Z, like dx, dy, dz, and that will give you the volume. Yeah. So again, don't be overwhelmed. But I mean, why this guy is important? Well, let me first explain to you what this guy is, because this is like the fundamental theorem of calculus in a vector form with like a vector function. So basically, what this guy is, like this omega A to omega B, it basically telling you what is happening at this surface here, for example, and what's happening at this surface here. So this like omega A would be like, for example, like from surface A to surface B. And basically what this equation is telling you like what is it changing at like your surface, like let's say this surface, and this surface is equal to what is it changing inside your like these volumes that you have here, like your representative volume represented, like this representative volume, what is happening at the boundary is equal to what is changing inside. And that's very simple. Like let me show you like what does this mean. Let's say I have like 10 units of whatever, like 10 units of contaminant, 10 milligram, 10 like grams of like contaminant or whatever, like entering this. And I have 8 grams or whatever, like leaving this. How many grams like stayed inside like this volume? So that's simple, like only 2 grams, because I have like 10 entering, 8 leaving, and what stayed here, like what accumulated here is 2. Yeah. If, for example, I have like 8 entering and 10 leaving, this means that like whatever contaminant was here is like decreasing. It's not accumulating. It's reducing. Yeah. This basically what this mean. Like this 10 and 8 are expressed by this guy, and this like accumulation or whatever is expressed like by this guy. But here again, remember, like we are not only considering what's happening along the x boundary, but we are also considering what's happening along like the so this is like your x boundary, and this is like your y boundary, and this would be like your z boundary. So we are also considering what's happening along like the z boundary, like something entering from here, and like along the y boundary, something like entering from here. That's why we have like this guy. So basically we are saying like I have a representative elementary volume. What is happening at my surface, like what's the fluxes that are entering and leaving my system, is equal to the fluxes that are either accumulated or reduced like from like my system. What is this called? Like, do we have a name for this? Just what I described? Let me describe it again. Let me say this again. The fluxes, like what is entering my system and leaving my system. So I have something and fluxes entering here across this whole boundary and leaving here across this whole boundary in 3D, like this boundary, like this boundary, this boundary, and this boundary. What is the fluxes that are entering and leaving is equal to the fluxes that are like accumulating in my system. Does this has a name? Yes, this is called the conservation laws of conservation. So the fluxes here could be like mass, it could be momentum, it could be energy. Wow, what does this mean? This is the laws of conservation of mass, momentum, and energy. So like all the, or not all, like most of these equations that we were studying when we were undergraduate students, like Bernoulli equation, for example, water chemistry, like it's in the structure analysis when you have like changes like in momentum. All this could be just derived from this guy, from like the laws of conservation. Like this guy is like the general form of all these other guys. Yes, yeah. Yeah, this guy is the general form of like most of these equations that you were studying, like Bernoulli equation, groundwater flow equation, Temnen transport equation, water chemistry. They can all be derived from this guy because this is the general law of conservation, and that's why these things are important in life. So let me just recap here. Basically, uh, like we have like this guy here. That's like the you can like flux that are like leaving minus the fluxes that are entering. Remember, like we did this before. That is equal to what is accumulating. So this is called like a surface integral. This is called like this guy I called you. This is called the diversion of u, and like which can be expressed as this. And in this module, like in this lesson, basically you will like we will have one lesson about vector calculus, and you will see how to do this and how to drive like how to use something like this, or like how to use this to drive the some of the familiar equations that you have seen like during your study, like Bernoulli, for example, like groundwater flow equation, like all this, how can they be derived from this? Okay, so that's all for this lesson. I hope it's not too long. If you don't understand much of this material, well, that's fine. Don't worry, don't panic. This is just like an overview of what we will be doing over the uh, next 8 week. So that's okay. We will go through every and all these things like in details,